All right, thanks. So I'm going to talk to you a little bit about curiosity. And when people think about curiosity, think about all the cool picture of the panorama, the geological features. But a lot of people forget that actually part of the goal of the MSL rover, the MSL mission and Curiosity, is to also measure things related to the atmosphere and the volatiles in the atmosphere, and try to constrain, like MAVEN would do, the history of the climate for Mars. So I'm going to try to give you a different prospect of what Curiosity does by showing you results that are not pertinent to rocks and geological morphology, but more about the atmospheric measurements that Curiosity does on a daily basis. So, as Bruce said, for those who attended yesterday's nice talk during dinner, Curiosity and the Mars Surface Laboratory mission is part of a large strategical big Mars program that have elements that build on each other. And so MSL came as a succession to the Mars exploration rovers and inherited a lot of technology and demonstration techniques that were used in MER, but also it's a precursor itself to the Mars 2020 and need to demonstrate how we can actually land on Mars, find a good site for a good sample to return to Earth. And that's pretty much the main goal of MSL. So MSL will be looking for habitable environments, try to find and understand the ways we should go about trying to find a good sample on Mars to return. A Mars return mission will cost billions and billions of dollars, so we don't want to go and grab just a rock and bring it back. So we want to make sure that we understand when we get there what we are looking for to characterize in order to bring the best sample humanity can get. And to do that, so MSL had four main goals. Obviously the first one is to assess past and present biological potential for Mars, characterize the surface geology and geochemistry, and these are the two goals that get the attraction of the people and the media, obviously. But also, actually, it does investigate the processes that influence habitability on Mars, which are mostly atmospheric driven. And that's where MSL gets to do the bulk of its atmospheric measurements. It's also, by itself, is a technology demonstrator where we get to demonstrate that we can put a ton, a 1 metric ton payload on Mars, be able to rove day and night for miles and miles, and being able to do complex sample analysis in situ. So all that's being done on a day-to-day basis in every operation we do. We think about making sure that we demonstrate the technology needed for Mars 2020. So, and to carry its task, MSL got a set of about 10 instruments and a little small toolkit. And these 10 instruments, you can divide them in three categories. The first category is for instrument that gives context for what the rover is sampling. The first instrument is the mass cam. That's pretty much what the camera that provides all the cool picture you find on the MSL website and all the nice panoramas. The Mardi camera is a descent imager that provides all the descent imagery when MSL was doing the entry, descent, and landing. And the MOLI, basically it's a small microscope that allows us to focus on very close to a rock and get very high resolution images of a sample. Then you have instruments that provides that basically assess the environment. The first one is RAD. It's a high energy radiation detector. It allows us to assess how much of radiation, harmful radiation makes it through the atmosphere of Mars and get to the surface. And this is actually very important for long duration missions, either for rovers. I mean, your electronics will be sitting on Mars. If you're planning to have a rover for 10 years roving, that rover will see radiation dose, cumulative radiation dose that will have to that has to be survived for 10 years. So it's very important that we understand what the radiation environment. And over the long run, for human exploration, you're going to send astronauts. As Bruce said and Nick said earlier, the atmosphere of Mars is very thin, so a lot of radiation can make it to the surface, and you want to make sure that you understand that environment so your astronauts don't get fried after a week. The second environmental instrument is the REMS. It's basically a meteorology station. It measures wind velocity, pressure, and temperature every day. And then we have a set of instruments that are more of provide the chemical analysis or composition analysis. The first one is DAN. It basically detects subsurface hydrogen-bearing minerals through doing a neutrons analysis. APXS, it's a contact instrument that provide chemical composition by looking at X-ray spectrometry. ChemCam, it's a laser desorption spectrograph that basically shoots a laser beam up to 7 meters ahead of the rover and ablates a part of the rock and look at all the hot gases, the composition of the hot gases that comes out of the rock. The ChemMin, it's a mineralogy experiment. They look at the mineralogy of the sample by doing the X-ray diffraction. And obviously my favorite instrument, SAM, is the sample analysis of Mars. It's probably the most chemical analytical lab ever flown to space. It's the size of a microwave oven, and it does dry and wet chemistry and allow us to analyze solid and atmospheric samples on Mars. So the two instruments, SAM and RAMS, are the core instrument that provides pretty much all the data about the atmosphere on Mars that we collect today. So I'm going to be showing you the results related to these pretty much two specific instruments. And finally, to drill, to sample, sieve, the rover has a little toolkit that contains drill and scoop and brush and a set of sieves. And it's very, very versatile, and it really does amazing things in how, with very, very fine precision. So, 1.5 years prior to landing, NASA down selected the landing sites to about 4, and the scientists got to sit together and agree on where to land this rover. All the 4 sites were deemed doable from the engineering point of view. It came basically to choosing the sites for science, and didn't take long to agree on Gale Crater as a landing site. Gale Crater had been actually part of the finalist for MER, for the landing sites for MER, and also was one of the privileged sites for ExoMars, the 2018 ESA rover. Gale Crater is located pretty much near the equator. It's about 150-kilometer crater that has about 5-kilometer mound in the middle of it. And from Mars Odyssey and MRO imaging, we know that that mound is highly stratified. And with clear, here zoom on this region where you can see the landing ellipse. You can see here this is pretty much where we landed. Just to give you a scale, this diameter is about, I think, about 25 kilometers. It's about 12 miles in radius. So we saw from space by using MRO and Mars Odyssey that there are very clean stratas, especially of clays and sulfates. I'll talk about that in the middle in a minute. And we have really, really nice, clean fluvial deposits. Basically, it was the probably remaining traces of a delta, where basically water, like Nick showed on the other picture, water comes out of the high plains and breaks the rim of the crater and create a delta where all the mineral deposits basically accumulates. So, and having these clay and sulfate strata actually point us to a specific time of the life of Mars. It's basically when Mars transitioned from being warm and wet and to the beginning of the dry and cold Mars of today. And so that mound in the middle of the Gale crater basically captured that transition. And that's where we think actually, like Janet talked earlier, where the Mars global climate changed. But the climate really doesn't yet, it started, obviously, you saw a dramatic change about 3.6 billion years ago, but actually the climate we have today on Mars is the result of a process that took about 4 billion years ago to accumulate. And we see basically the integrated effect of big processes and big changes, but also small processes that actually lasted for billions of years. And when you look at the integrated effect, can be actually as significant as bigger processes, but shorter in time. And here I took a nice graphic from Bruce's paper, where it shows over the 4.6 billion years of the life of the planet, all the big events that basically affected the atmosphere, from the hydrodynamic blow-off, where the hydrogen was entraining most of the atmosphere towards space, to the volcanic outgassing, to the exchange with the surface, etc. And what we try to do with MSL and obviously with MAVEN is not actually bring back or try to assess the atmosphere at one specific time, but actually to try to rewind the movie and look at what happens as the Mars aged. And the best way to do that is pretty much the entire scientific community agrees on, is to look at isotopes. Isotopes, probably most of you know that. I mean, most of chemical elements come in multiple flavors. You have a stable isotope, like for example, for carbon, it's carbon-12. It has 12 protons and neutrons, and then you have less abundant members of the same chemical elements that has 1 or 2 extra neutrons. So for carbon, you have carbon-12, that's the most abundant. You have carbon-13 is less abundant, and you have carbon-14 as actually radiogenic and decays to more stable, to the more stable form. And same thing for argon. We have argon-36, argon-38, and the more abundant argon-40. And so every process that basically interact with the atmosphere and change the atmosphere happen to actually leave a fingerprint in how by fractionating the isotopes, by privileging one member of the isotopic family against another. So all the basically processes that we may think about, from atmospheric escape that we know, like Janet talked about earlier, favors like isotopes, to exchange with a polar cap, what we call buffering, to the outgassing from the crust or deeper inside the planet, from radiogenic decay of radiogenic elements in the rocks. All of these basically leave an isotopic signature. And if we can read the isotopic signature in the atmosphere of Mars, or in the atmosphere that is embedded in rocks on Mars, then we can retrieve that record of the atmosphere at that time where the rocks was formed. So just to take an example of how this works, I took really a very simple example for xenon. Xenon is a noble gas, and noble gases have the merit of being chemically inert. So you don't have to worry about all the chemical processes that may alter what you're looking at. They're inert, and here I take an example of xenon. Xenon have isotopes, have dozens of isotopes that ranges from mass 124 to mass 136. It's actually abundant in the solar system. Here I put in the abundance in the solar abundance, like we see in the solar, we saw in the solar nebula and today in the sun. So you have the xenon abundance in percent, and obviously the most abundant one is 129. And that xenon that was in the solar nebula, when Earth formed, obviously we get that composition on Earth, but that composition then gets altered as Earth evolved and its atmosphere evolved, and the signature we see today on Earth is basically the cumulative effect of all these fingerprints that each process left, each process left over the course of 4.5 billion years. So I'm going to show you how we basically do the zero order analysis on Earth, and that's what we will try to do on Mars. So here you have the xenon abundance, the solar xenon abundance. We like to look at it usually relative to one of the isotopes. So instead of plotting it as percent, absolute percent abundance, we basically plot it as abundance relative to one member. Here we pick the non-radiogenic xenon 130. So we divide each abundance by this guy, and we find these numbers. For example, the 129 xenon is about 7 times the 130. Then what we like to look at, and that's how we quantify the effect of a process, is by looking at the delta from the variation of the rate, this abundance relative to xenon 130 from the solar values. So, and we express that in part per thousands, or what we call part per mil. And it's easily computed through this formula. You take your actual abundance, you divide it, the relative abundance, you divide it by the relative abundance compared to the solar values, you divide that by 1,000 and you get the deviation. So if you plot that for the sun, obviously everything will be 0. You're equal to the solar abundance. And then, so this is what originally came and formed the xenon that we have on the Earth atmosphere. But then Earth, about 500 million to 1 billion years into its formation, suffered a process called hydrodynamic escape, where the hydrogen, the atmosphere was dominated by hydrogen, the hydrogen was escaping, was hot and was escaping to space, and was entraining with it everything that was in the atmosphere. And obviously, it's easier to entrain things that are lighter than things that are heavier. So preferentially, the hydrogen was entraining the lighter stuff, and the atmosphere found itself more and more rich in heavy stuff. So when you plot the variation from the solar values, you find that the values gets higher for heavy stuff and get smaller or lower for lighter stuff. But then what happens over the course of the few billion years after, there were other processes that acted to alter this xenon distribution. One of them is, for example, xenon 129 got enriched because there is an element, the iodine 129, it's a radiogenic element that decays to make xenon 129, and that kept feeding the atmosphere, so that value went up. And then we have the plutonium 244, which is now, I think it's about extinct, produces through fission reaction the heavy species of xenon, and that enriched the part. And this is pretty much roughly what we see today on Earth. So as you see, the result we see today can be explained by looking at the fingerprint of each process. And if we can do this on Mars, for example, then we can retrace not only how much got lost through the ages by looking at just simply the isotopic, the current isotopic ratios, but actually by looking how, for species like xenon, what's that distribution look like, we can actually point out to specific processes that only them can combine to make the atmosphere that we see today. And that's the story we'll try to answer with MAVEN and MSL combined. So up to pretty much to 2007, 2008, by the time Phoenix lander landed on Mars, the only information we had, direct information we had about the atmosphere on Mars came from two sources. The first one, as Bruce talked about, the Martian meteorites. The Martian meteorites, when they formed, they had some glass inclusions that had some of the Martian atmosphere of that time trapped in them. And then those Martian meteorites made their voyage to Earth. And so today we're looking at, by sampling the gases inside these meteorites, we're looking at the atmosphere at the time where that meteorite formed on the surface of Mars. And the second source was the two Viking landers. They had on board a neutron mass spectrometer that sampled the atmosphere. The results were fairly controversial. We know today that the instrument did not have the capability to make very, very precise measurements. I think they basically created more controversy for about a couple of decades than solved problems. And using these two sources, basically, we know today that, for example, for xenon, to go back to the xenon case, the xenon on Mars, which is the black dots, is similarly fractionated as the xenon on Earth. So Mars atmosphere has the fingerprints. We know it for a fact has the fingerprints that actually what was left by all the processes that the atmosphere saw over the 4.6 billion years.
Can I ask you two questions?
Yes, please.
First, I'm going to ask you about Viking landers and meteorites. First, about the meteorites. How consistent from meteorite to meteorite are these isotopic measurements?
They were actually fairly consistent. I think Bruce will answer that better. You have a couple papers on that.
Yeah, I think that they've been able to measure the gases only in a couple of the meteorites, and they give similar results. The direct comparison with the Mars atmosphere, where possible, suggests that they're pretty accurate, and the measurements that Mehdi's going to talk about from Sam, I think, show that they're reasonably accurate as well.
All right. And, you said something about Viking. Can you go over that again? What this controversy was? I wasn't aware of this.
No, the value of Viking, basically, as I'm going to show you that a little bit in the graph later, have such a big, we know today they have such a big error bars that pretty much they didn't provide an answer. They made more questions than actually provided an answer at that time. So when we were designing MSL and SAM, the goal was really to make sure that we get the right precision, so we don't end up having to deal with a decade of discussion of whether the measurements are actually the deviation we see in the measurement are due to error bars, big error bars, or actually is a true value. And I'll show you that in the graph in a minute.
Okay, good. Thanks.
So to constrain the climate history of Mars, MSL will try to do three things. The first one is to assess the current state of the bulk atmosphere at the surface, to assess the current atmospheric exchange between surface reservoirs like the polar caps. You know, the CO2 and water on Mars freezes over at the poles and sublimates at the summertime, and so that there is a constant exchange with the atmosphere. And then try to look at ancient atmospheric records from rocks. As each time we take a sample, a rock sample, either we drill a rock or we take just a patch of sand sample, basically the rocks having them embedded the isotopic composition of, let's say, of carbon and oxygen that reflect the isotopic composition of the atmosphere at that time, plus the fingerprint of the chemical reaction or processes that make them get captured in the rock in the first place. So by looking at rocks, actually, we can also look at, get hints or get some of the state of the atmosphere when the rock was formed. But before showing you some detailed results of isotopic composition and bulk composition, etc., as I told you, Sam NSL actually had a weather station, and that actually provided us by itself a very nice results about the global atmospheric circulation on Mars. So we, as you know, the Martian atmosphere is about 150 times lower than the pressure, has a 150 times lower pressure than Earth. But on a day-to-day basis, here, for example, for Sol 31, Sol is a solar day on Mars, we call that a Sol, the pressure fluctuates by 10%. That's a huge amount compared to Earth, for example, where the pressure fluctuates between day and night about no more than 1%. And that big fluctuation we see during the day, it's consistent from day to day and is due to the solar heating that basically drive big tidal waves and that resonates, with which the atmosphere resonates. And so we get such a big variation. So we have this daily variation, we call the diurnal variation, but also we have seasonal variation. And here you have a comparison between Sol 31 and Sol 93, and you can see that the pressure jumped about 100 Pascal, so it's about 1 millibar over about 60 sols. And that's due to the exchanges we have with the polar caps on Mars. As the CO2 sublimate, it feeds into the atmosphere, increases the pressure, and as it freezes, it basically takes away from the atmosphere and lower the pressure. So MSL will be making these, make these measurements daily, and we'll keep making these measurements over the Martian year to basically look at the seasonal effects.
Where in the Martian year were these measurements?
So Sol 0 for MSL is the day we landed, which is August 6th of last year, and you have about 24 hours a day. So this is within a month after landing, so this was pretty much in November. What's the exact season? I think was I don't want to say something stupid, but I think it's a late spring, but I'll have to check for you and tell you that. And then this is a couple months after. And as the pressure fluctuated on a day-to-day basis, actually we saw the effect of that fluctuation on the energetic particle that were measured by the RAD instrument. So the correlation is actually very, very nice, and it basically can be explained by the fact that as the atmosphere gets thicker and the pressure goes up, the atmosphere acts as a shield and traps more energetic particles that are coming from the space, and less of them make it to the surface. But as the atmosphere pressure goes down during the night, these particles can make it much easier to the surface, and the energetic particle counts go up. So the atmosphere doesn't only have the variation of pressure of the atmosphere actually have an effect on how much radiation the surface sees, and it actually has also feeds in the story of how much hydrocarbons can be conserved at the surface of or in the few microns below the surface. These hydrocarbons get heavily altered by high level of radiation, so it was very important to understand what the variability of these energetic particles, not basically on average, but over a day and then over a season.
I just wanted to ask you about the previous slide again. You increased the pressure right now.
Yes.
Is that because it's warmer?
Yes, because we're getting, so it's a late spring, we're getting towards summer, it's the polar cap, the southern polar cap, I think it starts melting a little bit, feeding in the atmosphere, and the pressure goes up. So as we go in the winter, it's going to go down again. So, and to do for the elemental analysis of the atmosphere and the isotope ratios, as I said, most of the results are coming from the sample analysis at Mars instrument. This is about a 40 kilogram big microwave oven that makes pretty much half of the size of the payload on the MSR rover. And this instrument actually is not one, it's a suite of three subsystems that all work together to provide the measurement. The first one is a quadrupole mass spectrometer, and this is this is an analog to what we have on MAVEN. This is the analog of the instrument that we will be flying on MAVEN, the neutral gas and ion mass spectrometer, but this one was designed to operate at the surface. This instrument allows us to basically measure the bulk composition of the atmosphere.
And this goes to 500 mass units?
Yeah, it goes between, from the lighter hydrogen to mass 550, and it has a larger mass range to allow us to look for organics and complex molecules. We don't have to do that for MAVEN, because we don't expect to see any complex molecules up in the upper atmosphere. So we deliver to MAVEN a version that goes only to 150 mass units.
Okay, you still could detect simple organics.
Yes, but the instrument is pretty much the same.
All right.
The second subsystem is the tunable laser spectrometer. This tunable laser spectrometer was designed to look specifically for isotopes of methane and CO2 and water. So to look for, and that allows us to provide the isotopic ratio for oxygen, carbon, hydrogen, and to measure the level of abundance of methane. And it's basically that has a laser in it. We fill in this spectrometer has a little enclosure. We fill it up with gas, and then shoot the laser through the gas and see how much that laser gets attenuated in specific frequencies. And that attenuation is function of the abundance of that specific species or that specific isotope. So we can make extremely precise measurement up to 1 part per billion. And we were relying on that to provide the core isotopic composition.
That's what you need for argon, right? Because
that's what we need for argon. Actually, we can provide argon with this guy. This is what we need mostly for methane. And I'll come back to that methane measurement in a second. It really was the core measurement that the tunable laser spectrometer was after was methane, but it delivered a set of measurements that can be correlated with what the what the mass spectrometer does. So these two can actually confirm the results of each other, and so we have a more robust measurement. And the third system is a gas chromatograph. It basically measures the composition of evolved gases from rocks, or mostly from rocks, by looking at the time it takes for that gas or that element to travel through a very long and thin column, about 25 meters, 250 micron, and that's very characteristic to the species or the molecule you measure.
Okay, question about GC. What's the capability, if any? I think you have the capability to measure chiral contents.
Very little. It's not advertised as it's not part of the requirements that was by which the instrument was built. But there is capability to do chirality with this type of gas chromatography. It's literally those kind of results you have to be very careful in verifying before you advertise. First of all, you have to see chiral elements in the first place, and then try to see if you can infer any chirality with the setup, but it was not designed to do that. And finally to hold the samples, to carry them around, and to do all these complex processing. We have a sample manipulation system. It's a very complex set of 74 cups that we can use to put samples and carry them around and do these analyses.
Do you have any plans? When are you going to do the wet chemistry?
The wet chemistry is, just to explain to the audience, so we have a set of cups that have actually liquid in them. and that liquid is sealed, and that liquid is a special liquid that allow us to basically isolate very complex organic molecules. So it's a great asset that we only use if we have a first identification of really organics that worth doing that experiment for, because it's the kind of a consumable that you don't get multiple shots and using these cups for wet chemistry. So we didn't use any so far. We're waiting until we get a good first results on organics that worth doing this type of experiment. Then we will redo the experiments with wet chemistry.
So you have never considered using wet chemistry at John Klein or Cumberland?
No.
No. Okay.
So the instrument can carry a different set of experiments. About 3 of them are related to analyzing rocks and doing evolved gas analysis, but heating the rocks and getting all the vapors and volatiles out of it and analyzing it. But it has 2, and these are I think the most interesting for us here at the audience, is to do the atmospheric analysis. So it can do a direct atmospheric analysis, just suck in some gas, and through the mass spectrometer and through the laser tunable spectrometer, and look what the bulk composition is. But for specific noble gases and methane, we can do what we call enrichment experiment, where we take that gas and absorb anything that's not methane and noble gas in it, and then suck in more gas and keep depleting anything that's not methane noble gas until, so we keep enriching how much amount of methane noble gas, so we can get a better signal to noise ratio. And these allow us to get methane and for example, methane up to 1 part, 2 parts per billion, which is an extreme precise number. Both experiments were used on Mars. So we've been pretty much on Mars for 100 days and for about a year. And during that year, we traveled, so we landed in Bradbury landing site. You can see all the traces of basically the descent stage that messed up the area. Then we drove out of there. We went to an area called Glenneck, Yellowknife Bay, and then we're trekking back now towards the entry of Mount Sharp. But while we were driving, obviously Sam was not operating every day, was operating every so often. And we started, actually the first measurement we did with Sam were atmospheric measurements. And then we got comfortable with the instrument, we started doing some of the solid sample experiment, but we always kept doing atmospheric measurements. And this is to emphasize how important these measurements are for the goal of the mission. So we carry these experiments, the same atmospheric experiments at different time of the day, and we're trying to keep doing this as the season advances, so we can go through and see the seasonal, the effect of seasonal variation on the atmosphere. So far right now, I think this is a fairly accurate number. We did about 19 to 20 atmospheric analysis and about 12 to 13 solid sample analysis with Sam.
What's, I can't quite read it, the most recent solve?
365.
365.
Yeah, this is probably we
no,
shot.
I mean the arrow, that's where you made a measurement.
Oh,
yes.
this is where we made the measurement, the green arrow where I made an atmospheric measurement, and the brown arrow where I made a solid sample measurement. And actually, there's so much of them here that you don't try to count them.
Wait, the solid, that's the solid one from 354, I guess, is from John Klein at Cornell.
Yeah.
You just analyzed it. You analyzed it that day, but it's actually the previous sample from
yeah, we usually take a sample, we analyze it, we don't let the rover move until we're done analyzing it. Usually, that's the practice we've been doing. I cannot tell you really where the sample exactly was taken from. I think it's from this area, but what's the name of the rock, I cannot tell you that for now. Okay, so we did about, as I said, about 20 atmospheric analysis, and they all were consistent. They all gave pretty much fairly well-constrained result, and the consolidated result allow us today to provide a bulk composition of the atmosphere. We already knew that the atmosphere was dominated by CO2. What Sam found is that instead of what was reported with Phoenix, argon is more dominant, so the second gas in the atmosphere is not nitrogen. Nitrogen is the third gas, and then we have O2 and CO2 as the fourth and the fifth most abundant gas. The second result of the bulk atmosphere analysis is the fact that we were not able to detect methane up to the detection limit of about 3.5 part per billion. We need more analysis and accumulate more atmospheric runs to lower that detection limit to about 1.5 part per billion, but that's going to take time. But this is a very, very important result. As you all know, methane, the existence of methane on Mars has been advertised since the early 2000s, 2003, 2004, when some observation from Earth detected the values up to 230 part per billion of gas and methane, and then Mars Express went there. They saw some variation between no methane to about 35 part per billion. And the reason why everybody is hyped up by having methane on Mars is that on Earth we have methane, and the 95% of the methane on Earth is of biotic origin. It's basically the bacteria and the metabolism of bacteria releases methane. And only about 5% is from geological origin, basically venting through volcanoes and hydrotherms and the bottom of the ocean. So methane can be a sign of existent or extinct life on Mars. What's interesting about methane on Mars is that its lifetime is about 600 years. So if you don't have any source that produces methane, then methane will pretty much go away in a couple thousand years, and you'll never find it. You cannot regenerate it. So the fact that we can detect the methane on Mars, I mean, there is a source of methane that's maintaining that reservoir in the atmosphere, or that quantity in the atmosphere. Now, it can be of geological origin or from a biotic origin. Either way, it's very interesting finding. If it's from a biological origin, that's it. If it's from geological origin, then it's mostly hydrotherms, and that means the water, there is liquid water interacting with rocks to make this methane today. And so going after the methane was a big thing for MSL, and that's why we designed SAM to specifically target methane. Unfortunately, or fortunately, I don't know, up to today we were not able to detect methane. Maybe it's a seasonal thing. Maybe it appears somewhere in the Martian year and then get captured in another reservoir for the rest of the year, and so you have to wait. So we'll be tracking this measurement for the rest of the mission and see if we can actually detect methane and if we can pinpoint it to some origin. The second results is from SAM is the isotope of carbon and oxygen, and specifically the ratio between the deviation of carbon-13 to carbon-12 from terrestrial values, and the deviation of carbon-18 to oxygen-18 to oxygen-16 from terrestrial values. And here I put in the values that came from Viking GCMS, NMS, the meteorite gases trapped in the meteorite, Martian meteorites, and the Phoenix Tiga measurements. And you can see what I was talking about earlier. The Viking GCMS found that the deviation, the terrestrial carbon isotopic signature, the Martian isotopic signature on Mars is the same as terrestrial. There's zero deviation. But look at the error bar. It's humongous.
It's humongous.
It's a humongous error bar.
It's like 100%. About reading it, right?
Sure. And so Phoenix Tiga got some measurements, but they was not really designed to do those kind of measurements, so was pushing the instrument a little too far. So SAM came and provided the numbers with very small error bars, and you can see that the SAM results are actually very consistent with the gases we found in the Martian meteorites, with a very a narrow, small error bar, and a very consistent value from run to run.
Yours is about 5 or 10%. It's about hard.
The error bar?
Yeah.
No, these are about 50 per mil, and the error bar is about 1 or 2 per mil. Go ahead.
So my question is, you said on the Phoenix one, you said that you were pushing the instrument sort of to do something that wasn't really designed for pushing the edge of it. So how come the error bars are so small and the number is so totally different from what you got with the SAM?
Very good question. So the TIGA instrument was really designed to analyze solid samples. They did measure did measurement of atmospheric gas, but after the fact they had solid samples in experiments, so we don't know how those values got contaminated. There was no cleanly, like SAM is designed to basically, when it does an atmospheric run, it doesn't carry any contamination from any past measurement, whether solid, etc. So you don't know how these values moved.
So the error bars are then based on its consistency with itself?
With itself is the measurement precision.
Your actual, they're not confidence bars, they're error on the measurement.
It's error on the measurement,
Okay.
It's instrumental error.
Good, thank you.
So I took another nice plot from one of Bruce's papers, where he actually, as I told you, the isotopic ratios have fingerprints of what the loss process of that element. So here, if you plot the deviation of carbon-13 and a deviation of oxygen-18, it depends on the value you get. You can actually tell what processes contributed or was the driver behind the loss of oxygen and carbon. So it was very important for us to take those carbon-oxygen measurements and drop them somewhere on this graph and see what we find. And it comes there. And it comes in a quadrant where we think that the carbon and the oxygen were lost dominantly to space. So this is a very important result, but that was not the only results. We looked at, I'm sorry, go ahead. Oh, yeah, sure.
I thought you were going to put some more data up.
Oh, no.
This is a field where you only get one data point.
Yeah. And then you wait 20 years. But that was not the only isotopic composition that led us to think that the atmospheric gas was lost to space. We took the measurement for argon. Argon is another noble gas, no chemical, is chemically inert, and we looked at argon 36 ratio to 38. These are not the most abundant argons, and argon 40 is abundant, but argon 40 can also get messed up by decay of radiogenic potassium. So these are stable and non-radiogenic isotopes. So we look at the ratio. We know the ratio. The Sun, we measured the ratio at Jupiter with the Galileo probe. We know the ratio at Earth, and they're all fairly consistent around 5.5. The Viking value had a humongous error bar, so that was not really conclusive. And the meteorite pointed us toward an atmosphere that's more enriched in the heavy argon-38, and with SAM comes to actually confirm that value. So we're dead on with the measurements from the meteorite to about 4.1, 4.2. So compared to Earth, the argon on Mars is enriched in the heavy element, and that points to loss to space because argon cannot really get lost anywhere else. The last value, and Nick and Jana talked about a little bit, is the ratio between deuterium to hydrogen. These are the two lightest elements of the elemental table, and they have a factor of mass of 2. And from Earth observations, we know that the ratio of deuterium to hydrogen varies with the seasons. It varies with how much water is suspended in the atmosphere, in micron of precipitable water. MoMA did a lot of work tracking how much that ratio versus the precipitable water over the different seasons. So each profile is a different season on Mars, and SAM TLS measurement came to put us pretty much at an average value consistent with the observation, and this is a value that pretty much, it comes from a rock measurement and rockness, so it's not directly from the atmosphere. So we think it represents a seasonal average that was captured in a rock. It's not in the actual value in the atmosphere, but it's consistent with deuterium to helium ratio that points to escape to space. So we're still carrying more atmospheric measurements with the MSL. The next step would be to try to nail the nitrogen 15 to 14 ratio, try to look at the heavy noble gases, krypton and xenon. These are even rarer in the atmosphere gas, so we have to enrich and integrate for longer time, and keep looking for that methane. Try to either rule it out or have an upper limit, but look over variation over seasons. So the results of, basically in a nutshell, of everything I said is that the in situ data from MSL support the hypothesis of substantial atmospheric loss that was dominantly to space. So when MAVEN comes into the picture, will allow us to provide the data needed to determine the extent of that loss, how much really we lost. We know what's the atmosphere state today, but we don't know what was the atmosphere before, so we have to assess how much the cumulative loss over the billions of years, and the chronology of that loss. How did we lose it? Was it over 3-4 billion years, or was it one event, or how did it work? So here, our MAVEN. And MAVEN will look at trying to answer 3 questions that are complementary to what MSL is doing. The current state of the upper atmosphere, as you know, MSL is looking at the lower atmosphere. The current rate of loss to space, since now we know it's confirmed that this is probably the dominant escape mechanism, and try to derive the integrated atmospheric loss. And the great thing is we can have these 2 missions, 2 assets at Mars at the same time. MAVEN, I guess, Bruce, when it was proposed, there was no plan to operate when MSL was there. I don't know. You tell me.
You can't propose assuming MSL was going to be there because of the risk of failure of one or the other.
And MSL was not supposed to have MAVEN in there too. So it's great today to have the 2 assets, and the great thing is, as I said, MSL will measure the composition of gases at the bottom of the atmosphere, while MAVEN is doing the same measurements on the top of the atmosphere. And by combining the 2 set of measurements, we'll have an integrated look on the present atmosphere and escape processes. But also MSL will look at the composition of ancient atmosphere on the rock by keep drilling and looking at these solid samples. While MAVEN will look at the impact of variation of the escape processes, what the variation of the EUV input will do, what the variation of the solar wind speed or solar wind density will do on the escape process. And by combining this together with combining that with the actual state of the atmosphere, we can rewind the movie and be able to decipher the history of the atmosphere and climate on Mars. But the last thing, and probably the most exciting thing for me from an engineering point of view, is that these 2 spacecraft will chat together. As Bruce said, we carry an Electra package that allow us to talk to MSL, and for me who participate to daily operational SAM, and we waiting for downlinks for Mars Odyssey or MRO to get our data, to be able to get my data from MSL through a spacecraft where I have another instrument. It is a lot of exciting things. So MAVEN will pass by every day and ask the question, and MSL will get the answer. All right, thanks a lot. Any questions?
So how often will
like Bruce said, we can have the neutral, you're talking about the neutral gas mass spectrometer specifically. We will be operating on every orbit during the periapse, and we have an orbit every about 4 hours and a half, so we'll get about 5 to 6 data sets a day.
So the instrument doesn't really degrade much over time?
MAVEN.
MAVEN's instrument.
As all space instrumentation, they do degrade over time. The space environment is extremely harsh. For example, just give you an example for the neutral gas mass spectrometer, we have hot filaments that allow us to ionize the neutral atmosphere, makes ions. It's easy for us to detect ions than to detect neutrals, so we ionize them. And those hot filaments, as any light bulb, basically one day it's gonna break. You know, they get thinner and thinner and thinner, and then you burn them out. We have multipliers, these particle detectors that age as you bombard them. The more you bombard them, the more they age. So we keep measuring by bombarding them. That's how they actually measure. And so they will deteriorate with age, but you never know. You build an instrument to meet a requirement of life, like Bruce said, of a nominal mission. You hope for an extended mission. But if I take an example, and Janet will probably concur, we have a similar instrument on Cassini that's been running since 1997 and still doing wonderful science. So you never know. I mean, what you hope is the instrument will last as long as you can, and as long as possible, but we'll take every bit of data we can.
Oh, how does the enrichment work in samples?
We have these getters. Basically, these are solid gas traps. They basically have affinity to trap specific molecules. So we have a getter, for example, that since the atmosphere of Mars is CO2, we want to obviously getter the CO2. So we take a slug of gas from Mars, we put it through the getter will suck everything out, included water and CO2, but it doesn't do anything for noble gases or hydrocarbons. And so they will stay there. Then we take that little gas, we put it aside, we take another slug of gas, we suck the CO2, and then we add them together. And we take another third, and so we keep adding more and more and more and increasing the pressure of the noble gases. Once we reach enough pressure, we just put them in either the TLS or the mass spectrometer and take them in. So that's an enrichment, and that allows you to get better signal-to-noise ratio and get your detection limit below what you normally do.